Dr. Zellem, thank you so much for taking the time out of your busy schedule to talk with us today about how you got such a cool job at NASA at the Jet Propulsion Lab.
Yeah, thank you so much for having me, and happy Friday, everyone, hence the Hawaiian shirt today. So yeah, really appreciate it. And thanks to everyone who's attending today. So take it away, I guess?
Yep, take it away.
Sounds good. All right, let me share my screen. And let me get two things out of the way first. First off, yep, I work at NASA's Jet Propulsion Laboratory. This is the same lab that recently landed that rover on Mars. And answer your questions already. No, I did not work on the mission. It was super cool. I was super excited to see it. I have friends that worked on it, but I unfortunately did not. It was pretty cool though. And also, second, my condolences to the Kansas City Chiefs. I was rooting for them to win the Super Bowl, even though I am a Tennessee Titans fan. As you'll find out, I grew up in Nashville, Tennessee. So despite that AFC rivalship, I was rooting for the Chiefs to win. So my apologies on that. So as that great intro said, I am Rob. I work on exoplanets, and ultimately what I want to do, I'm a giant Star Wars nerd. I love science fiction, and I want to find aliens. I want to find life out there in the galaxy. And this love of science, of NASA and astronomy, has been something that, I've been interested in pretty much my entire life. Right here is a picture of little young Rob meeting his hero, the astronaut at Kennedy Space Center. I get asked a lot if I ever wanted to be an astronaut, and I have to give it a hard no on that. I am deathly afraid of heights. So that pretty much rules me out from joining the space program. But I do what I think is the next best thing. I work for NASA, and I get to study things safely from ground level. So as I mentioned before, I grew up in Hendersonville, a small town outside of Nashville, Tennessee. I'm a big Titans and Preds fan out there for NHL fans. And growing up outside of Nashville, I spent many summers at the Adventure Science Center. This was my local science museum. Back then it was called the Cumberland Science Museum. And I did science camps, loved going to the planetarium, to the exhibits. And that was one of the ways that that love of science and astronomy really was instilled for me from a young age. And I just never really grew out of it. I always really loved astronomy and NASA. I think I actually had space wallpaper on my wall with space shuttles on them growing up as a kid. So it's really now being able to work at JPL is a dream come true. So this love of astronomy just really stuck with me throughout grade school, middle school, high school even. And with that, I decided then to major in astronomy. So I got my undergraduate degree at college in astronomy and astrophysics at Villanova University. If you've ever heard of this college, you've probably heard of it thanks to their basketball team, which is pretty good. And that's outside of Philadelphia. I got my undergrad Bachelor of Science from there. And then I decided to shake things up and go study abroad. So I actually spent about a full calendar year in London, England, in the United Kingdom, where I studied and got my Master's of Science in Space Sciences at University College London, also known as UCL. Then after that, I came back to the US. After stocking up all that rainy weather, I dried out in the desert at the University of Arizona in Tucson, Arizona, so Southern Arizona, where I got my PhD in planetary science. So in undergrad, I studied a lot about stars and variable stars and sort of classifying and characterizing stars and how the stars basically change over their life cycle. And at the end of my undergraduate school career, as much as I loved looking through telescopes, I was really inspired by these planetary scientists who could actually build a robot like Perseverance and Curiosity and actually send it out to the planet they want to observe and study. And they can actually send their object or their probe there and actually basically study their planet close up via these probe measurements. So that really inspired me to do sort of a shift. And instead of getting my PhD in astronomy, I ultimately decided to do it in planetary science, which is the study of planets, including the Earth, but stuff in our solar system, including exoplanets. These are planets outside of our own solar system. So I went to U of A, the University of Arizona, to get my PhD in planetary sciences. I originally thought I would be studying Mars or Europa, but basically as soon as I got there, I realized very quickly that I missed telescopes. So I did another shift again, and I decided to specialize in exoplanets, which I'll be talking about today. After that, I was very fortunate. I was able to get what's called a postdoc. This is typically a 2 to 3 year period after you get your PhD, where you sort of find your own footing. And I got it here at NASA JPL. And now about, let's see, 5 years later, I've been here, 6 years. I am now actually a staff member here at JPL. I'm an exoplanet astronomer. And here's a picture of JPL. Clearly this image was taken many thousands of years ago, back when LA had water in the area. We have that really nice cloud level or snow level up here. And the building I work in is right here. It's pretty cool. I love JPL. It reminds me of basically a college campus with a ton of nerds on it, which fits me perfectly because I'm definitely one of those people. And unfortunately though, due to COVID times, most of us are working from home. But at JPL, as I mentioned before, I am what's called an exoplanet astronomer. So let's unpack this really quickly. Exoplanet, you might have heard of this term before, and what it really is short for is extrasolar planet. Let's unpack this a little bit further. So extrasolar means anything beyond or outside our own solar system. In our solar system, we have the sun, we have 8 planets, 8 because Pluto's not a planet, right? So anything beyond our solar system is extrasolar. Anything outside of our solar system is extrasolar. And planet, well, that just means planet. And those of you who don't remember what a planet is, it's basically, any small body roughly the size of Jupiter or smaller. And then therefore, an exoplanet is any planet outside of our own solar system. And then I'm an astronomer, and hopefully some of you know what this means. This means that this is someone who stares at the sky, or more likely their computer for way too long. And as an exoplanet astronomer at JPL, what I do is I work on telescopes, I work on missions, I work on data to observe extrasolar planets or exoplanets, planets outside of our solar system, to ultimately answer that ultimate question: are we alone in the universe? Because I want to find aliens. You can see up on my posters behind me, I have a space shuttle up there on the 747. I'm a huge NASA nerd. I love Star Wars as well, and I want to ride the Millennium Falcon, guys. In order to ride the Millennium Falcon, you got to find it first. So I'm trying to answer this ultimate question: are we alone in the universe? So the question is, how do we find these exoplanets? And there's actually a bunch of different methods. I'll be focusing quickly today on these two. And these are both very near and dear to my heart because I work on them at JPL. So I'm contractually obligated to talk about them. The transit method right here. Let's take a quick look at that. So when we're looking at a star with a telescope, if there's a planet orbiting around that star and it has the right alignment, if we're lucky, that planet will pass in front of its host star and block out some of the star's light, causing the star to dim. As you see, as we're measuring the light of the planet, or the star, the planet gets in the way and it effectively casts a shadow on the Earth, and it causes the star to look a little bit dimmer. The amount of light that that planet blocks out as it passes in front of its star directly tells us the size of that planet. So for example, a big planet will block out a lot of light, whereas a small planet will block out just a little bit of light. So the amount of light that's blocked out during a transit directly tells us how big that planet is relative to its host star. And this method has been used to discover over 3,000 exoplanets, a majority of the ones we know today. And I use this transit method mostly as a PhD, during my PhD studies, but also now at JPL, to characterize and observe exoplanets. This method is great because it's actually relatively cheap. You can actually do this with a small 4 or even 6-inch telescope. I actually saw a post on Reddit a few years ago while someone just used a digital camera to observe a transit from the ground with no telescope at all. And this allows us to measure the size of the planet. But you have to have that perfect geometry. In order for the star to be dimmed by the planet has to pass in front of the star relative to our line of sight. So the planet has to pass in between us and its host star. If the planet is orbiting around the star in this geometry, the planet never passes in front of the star and doesn't block out the star's light. But the transit method is extremely, extremely crucial and also a fairly popular method to characterize exoplanets. So for example, the Hubble Space Telescope has already observed tens of exoplanets to characterize their atmospheres, to figure out what molecules, what elements are inside the atmospheres of these planets. James Webb, the JWST instrument or a mission or telescope that I'll be launching hopefully in the next few months, that it is the successor to the Hubble Space Telescope. This telescope is ginormous, to use a scientific term. They're actually doing some testing out here in LA, and pre-COVID, I was lucky enough to actually see it in person. This mirror is about 6 meters, which is roughly 18 to 20 feet across. This purple thing on the bottom is actually the sun shield. So it actually shields and puts the main telescope in a shadow caused by the sun shield. That sun shield is actually the size of a tennis court. This observatory is so giant that it actually has to fold in like origami and then unfold itself just to fit inside its rocket fairing. So in order to even fit it on the rocket, it has to fold it up on itself. It's launched out into space, and then it goes through this very complex unfolding process. I also work on a mission, a European mission called Ariel. This is run by the European Space Agency, or ESA, which is basically the European equivalent to NASA. And there's actually a NASA instrument on board that I've been able to work on for this mission. And that mission will also be observing transits. But if we want to use these telescopes to observe a transit when the planet passes in front of the star, we have to know very precisely when that transit will occur. So for example, if there's a 15-minute uncertainty of when that planet passes in front of the star, that's an extra 15 minutes that we have to build into our observing sequence, our observing scenario, in order to make sure we actually catch that transit event. So 15 minutes doesn't sound like a lot of time that's wasted, but it actually is, because any time wasted on any of these instruments is extremely precious and extremely costly. So what we want to do is we want to use these instruments as effectively and efficiently as possible. So we need to know that timing precisely. And this is where small telescopes can come in. Small telescopes, 4-6-inch telescopes, can actually observe a lot of these transiting exoplanets, help us refine that timing, and enable large telescopes to follow them up a lot more efficiently. This is actually a data set taken with a small 6-inch telescope from Tucson. And this really indicates that small telescopes run by amateur astronomers and citizen scientists can actually contribute to NASA science and missions directly. And this inspired us to launch a new citizen science project called Exoplanet Watch, where we invite citizen scientists to help us monitor transiting exoplanets. If you have your own telescope and camera, we are looking for beta testers right now to help us test our software and all of our website and our data upload and all that. If you're interested in becoming a beta tester, just go to the URL at the bottom, or alternatively, you can just Google NASA Exoplanet Watch, and we should pop right up, and there'll be a lot of information on how to join on our website. If you don't have your own telescope, we'll be launching officially in June, around then, this summer, and we're thinking of ways to basically hand out some robotic telescope time that we have, enabling you, even if you don't have your own scope, to participate in our project. So if you're interested in joining or participating, please stay tuned to our website. I actually use, as was said in that awesome introduction, some instrumentation local in my area. One instrument is NESI, which is the New Mexico Exoplanet Spectroscopic Survey Instrument, or NESI. And it's right here at Palomar Observatory. This is the 200-inch telescope, or the 5-meter telescope at Palomar, just outside of San Diego in Southern California. This was, for a time, the world's largest telescope for about 50 years. And this telescope, which was built in 1948, was built even before we had, 50 years before we even discovered the first exoplanet. So it's incredible, by just basically putting our instrument on this telescope, we can enable exoplanet science. So right here is actually a picture of the NESI instrument. No, that's a mythical sea creature. Sorry, let me get the right photo. Here we go. Here's a picture of the NESI instrument at Palomar Observatory. And we are now starting to get some measurements of transits of exoplanets. This is an instrument we're actually commissioning right now over the last 2 to 3 years, and hopefully we'll be making routine observations all the time. So that's how we can find exoplanets with the transit method. The other method I use at JPL with some missions I'm working on is the direct imaging method. And just as it sounds, this is literally taking photographs of exoplanets. But there's a problem. If you want to take a snapshot of an exoplanet, we have the star nearby. And the stars are generally much, much, much brighter than their exoplanets. So for example, let's take a sun-like star, and let's throw around that sun-like star a large planet that's really hot and therefore really bright, a hot exojupiter. Well, that planet is still 1,000,000 times fainter than its own star. That's like looking for the light of a firefly around a lighthouse, and you're looking from the East Coast to the West Coast. But the ultimate goal is to look for aliens, to look for life, to discover planets that could host life, Earth-like planets, for example. If we take an Earth-like planet, and we put it around that same sun-like star, that Earth-like planet is 16 billion times fainter than its own star. That's like looking for one bioluminescent alga around that same lighthouse. So how do you block out the star's light? Well, if some of you saw the solar eclipse that happened a few years ago, what you can do is you can think of a way to block the star's light to then uncover the light from the planet behind it. And that is exactly what we're able to do with hardware. We're able to put a mask in place called a coronagraph, block out the star's light, and make the smaller or the dimmer light from the planet a lot more visible. And this method has been successfully used with large telescopes, 6, 8, 10-meter class telescopes from the ground. So what we're showing here is actually an animation of observing an extrasolar solar system. This is 1, 2, 3, 4 planets orbiting around their host star. This was taken by the Gemini telescope here on Earth, an 8-meter telescope. You can see right here, there is the disk from the coronagraph blocking out the star's light, enabling us to uncover the light from the planets themselves. And this method will be used by the Nancy Grace Roman Space Telescope. This is a mission that I work on here at JPL. One of the instruments on board is used for direct imaging. And this instrument is called the chronograph instrument, or CGI. So Roman CGI will allow us to basically go from where we are currently, which is looking for hot, bright, large planets far from their star, to get where we want to go, which is small, dim objects close to their host star. And what Roman CGI will do will provide that stepping stone by allowing us to observe things that are closer to their star, but also dimmer and cooler as well. So this will demonstrate that the technology that works so successfully on Earth will also work in space. And it'll enable us to go from this step to this step. And then those lessons learned that we make with CGI will allow us to build missions in the future that will allow us to observe exoplanets that are very much like Earth and that might actually host life on them. So in summation, I work on a bunch of different missions here at JPL. I do a lot of ground-based science. I've actually used data from Hubble and Spitzer to characterize exoplanets. I can talk more about that later. We're actually about to enter into a next phase with the launch of the James Webb Space Telescope and Roman, used to be called WFIRST. And this will allow us to start observing planets that are smaller and dimmer and cooler than ever before. And then the next batch of NASA missions, these are missions that will be launching hopefully in the 2030s and 2040s. These are missions specifically designed to look for small planets that might be habitable. So we're really now sort of in this golden age of exoplanet science. It was pretty incredible that I got to really witness basically the birth of this science in the late 90s. And now we're routinely making exoplanet observations with ground-based telescopes, with Hubble, previously with Spitzer. We'll be making them routinely with James Webb, with Roman, with Ariel eventually. And then those next generation missions that are under consideration from NASA to be launching in the 2030s and 2040s and beyond, they'll be potentially able to finally answer that question, are we alone in the universe? And with that, I'll stop talking. I'll be happy to take your questions. Thank you so much.
That's fascinating stuff, Dr. Zellem. Let me ask you about the James Webb Space Telescope, though. I've been hearing that that's ready for launch for over a decade now. Is it really going to happen this year?
The latest news that I'm hearing is October, I think, of this year. So hopefully it stays on track and we're not impacted by anything. Yeah, because that'll give us unprecedented precision, and it'll also allow us to really expand our wavelength coverage. So right now with Hubble, we're limited in the wavelengths of light that we can look at, and therefore we can only look for certain molecules in the atmospheres of these planets. James Webb will expand that wavelength coverage and enable us to look for other molecules potentially for the first time. So it'll be really a huge game changer.
That'll be exciting. If you have a question for Dr. Zellem, ask him anything about exoplanets or classwork, anything you want to know about how to become a professional astronomer. Just you'll see the Q&A chat box at the bottom of your screen. Type them in there. If you're on Facebook, type your question in the comment section. I'm monitoring Facebook on the other screen here. Let me start off with a question about your transition from college to the Jet Propulsion Lab. Now that you've been working in the astronomy field, does your day-to-day work match kind of what your concept of being an astronomer was back when you were in school?
Yeah, so like I thought I would, as a high schooler, I sort of naively thought that I'd be using a telescope all the time. And that was sort of like this romantic notion that you would be just, continuously at the observatory and observing. And luckily for my sleep schedule, that's not the case. I'm actually usually at my computer most of the time, doing a lot of data processing and analysis. So that's what I mostly specialized in grad school. I would go to the telescope, every so often, but a majority of my time was, sitting in my office in front of my laptop or my computer and taking those raw images and processing them a lot to produce these measurements. So I specialized that in grad school, and now at JPL, I really had the opportunity to sort of branch out and try new things. It's been really, I've been really lucky that I've been able to have that opportunity. So I've been working on anything from helping develop instrumentation to working on NASA missions to still doing research as well. So now a lot of my day is still mostly on my computer as well. I still occasionally do get out to the observatory, but it's also in lots of meetings and helping to basically figure out how to make these instruments work to achieve the science we want them to achieve.
All right, we have a question from Thor, excuse me, who wants to know how many years did it take you to finish all of your degrees?
A long time. I was in school until I was 29. So let's see, undergrad was 4 years, my master's was 1, and then PhD was 5.5. So long time.
And to get a job like you've got right now, are graduate degrees required?
For scientists, typically, yes. A PhD is typically one of the requirements, but also some people do get their masters and do quite well. For engineers, it's definitely a different story. JPL is mostly engineers, actually. I'm one of the few scientists on lab, and they can come straight out of undergrad and work directly at JPL. And to answer Holly's question, you do not have to be a US national to work at NASA JPL. You can be a foreign national, for example. Having a green card definitely does help and all that. There are security issues. There are some ITAR restrictions if you're not a US citizen, for example. Qualifications to be a scientist at JPL is typically, as I mentioned, having the PhD is super helpful, potentially your master's. And then I think someone else asked about programming challenges. My background is that I was quite adept at computer programming. I knew C, C++, Fortran, IDL, MATLAB. Here at JPL, I'm mostly doing all of my coding in Python. So if you know lots of Python coding and can do that, that works out pretty well too. Someone can type in the chat if it's me that lost the link or nope. Okay, looks like we actually got disconnected with the library. That's fine. I'll keep on forging on. Can someone just type in the Q&A if they can still see or hear me? That'd be very helpful. Or in the chat. Oh, I am seeing some answers in the Q&A. Great. Thanks, everyone. Appreciate it. Okay, I'll just forge along then. Awesome. Okay, so how to become an astrobiologist? That's a great question. I really don't know. I think there are astrobiology programs around the country. So I'm a planetary scientist. I wouldn't call myself strictly an astrobiologist. And so that's more of the biology, the chemistry background. I'm more of the physics, math, science, astronomy background, Jose, to hopefully answer your question there. How can you apply to JPL as a PR holder? I'm not really sure what you mean by PRAH. So if you wouldn't mind, just quantify that or clarify that in the chat, that'd be great.
I got kicked out of Zoom, so
no worries. We forged on.
I'm glad the connection was still going there.
Yeah, so Harris is asking how, if I have any advice for how high school students can get an edge in the field. One of my biggest things of advice is to learning programming is really helpful. Specifically, Python seems to be the new programming language of choice that people are using. So if you have a really strong high coding background, that helps out a lot. Typically also, having that drive to do any project, to work on any task is really important. And those who have that drive, even if they lack the background information or knowledge, people like that can, basically pull themselves up themselves, teach themselves what they're lacking, and to participate and to excel. So for example, in high school, I actually failed one of my physics midterms. And rather than freaking out about it, I worked really hard. I passed that, and then I just kept on working really, really hard throughout my entire career. And that sort of gumption, I guess, is what enabled me to continue working on and to basically get my job here at JPL. Thank you, Fernando. So permanent resident, yes. So basically on any of the NASA centers, there is a NASA job site. I forget the URL. You can Google it, and they have job postings all the time, and they actually specify in there if you have to be a US resident or a permanent resident or a green card holder. So I would take a look at the NASA websites there.
Did you have any interns when you were in high school or college?
When I was a high schooler, no. In college, yeah, I did some internships. I did a program or two, and that's another great way to sort of get your foot in the door. I know a lot of people that do the JPL engineering internships, for example, in college. Some of those people do actually get hired directly out of undergrad as early career hires. We also do hire interns as well. The website, if you're interested in doing a JPL internship, and if you are at least in college, unfortunately, they don't do high schools, at least I don't think for the summer. Just Google NASA JPL internships. That should hopefully pop up. I think it's jpleducation.jpl.nasa.gov. And there should be lots of internship opportunities you can take a look at. So we're also getting lots of questions about entry-level telescopes. What's a good one? A good one is anyone you can afford. Honestly, I got started on a small little telescope about 3-4 inches in diameter. My parents actually got it for me off their credit card points. And that was still enough to see the rings around Saturn and really inspire me to become an astronomer and keep on going with it. We're in our own citizen science project, some preliminary figures are showing that you can even do transiting exoplanet science and observations to something as small as a 4-inch telescope. And we're hopefully making our citizen science project to really allow people to use those telescopes to participate in our exoplanet project.
And let me tag on to that. William asked about any books or reference guides. Perhaps I would suggest, I don't know off the top of my head, but go to your local library and they'll be able to help you. And if you're in the Kansas City area, there's a wonderful astronomy club. It's called the Astronomical Society of Kansas City. They're a very active group, and they love teaching new people how to get into astronomy. And I'm almost certain, I think a town of any size will have a local astronomy group that you can reach out to, and they love helping people as much as they do looking at the night sky.
Yeah, totally. So definitely reach out to your local astronomy club if you don't have one, or also definitely reach out to your local library. One book that I hear excellent things about is one called Turn Left or Turn Right at Orion. It's one of the two directions by a guy named Guy Consolmagno, and he just has a really excellent introduction on how to do ground-based observing with small telescopes.
He's the Vatican astronomer.
Yep, he was one of the reasons that I got into planetary science. So I went to a summer school program with him and got to meet him and spend time with him. And he's one of the reasons I became a planetary scientist.
That's good stuff. Yeah, he spoke at the Linda Hall Library a few years ago. So,
oh, nice. He's an excellent public speaker.
Yes, wonderful. I can see how that would he would inspire you.
Oh yeah. So I'm getting another question about 55 Cancri E. I have studied a little bit, but not too much in depth. So I know the latest observations of it indicate that it's probably a lava planet. So it's likely very, very hot and actually might have lava on its surface. There's actually a really cool poster of 55 Cancri E released by JPL and its art department. If you just Google 55 Cancri E JPL NASA travel poster, that should pop up. It's actually, it's a cool artist's impression. If humans were to visit this lava world, you know, how could they survive safely on that surface? What is my favorite project that I have worked on, Carolyn? It's whatever I'm working on right now because they're paying me. So I'm legally obligated to say that. No, honestly, I'm really lucky that I get to sort of pick and choose the tasks and the projects that I'm working on at JPL. And it's a lot more fun to be working on things that you're excited and interested in doing. So working on direct imaging was something I always heard about as a graduate student at University of Arizona and saw my friends working on it. And I've always been interested in doing it. And now I'm really lucky that I get to be involved in this project and actually work with some of my friends from grad school on direct imaging. So that's a blast. And working on any missions, I've been able to work on Ariel and CASE, which is that NASA contribution to the ESA mission. And working on missions has been a lifelong dream of mine. So that really, really is a ton of fun. And I'm really excited to hopefully see a launch of, you know, an instrument or a mission that I worked on from, you know, either the East or West Coast.
Let me ask you a question, Dr. Zellem, about schoolwork. You know, you have an impressive list of degrees, especially your undergrad, a BS in astronomy with a minor in physics, mathematics, and classics.
Nerd.
I don't think there's an easy major in any of that stuff. How did you develop the study skills, you know, to handle those really tough classes and kind of tune out everything else that comes along with college life?
That is a great question.
Any helpful tips?
I don't know, just to keep on keeping on, I guess, and just to not give up. So for example, you know, I had trouble initially with physics, and despite, you know, not doing so well initially, rather than let it discourage me, I decided to, you know, really buckle down and work hard to overcome that and to then excel, I guess, in the class. So really it was just having that drive going forward. So despite, you know, I'm not the smartest person in the room, I'm not the brightest person, I'm not the best coder, but I like to think that I work really hard, and having that drive is what really helped me to really achieve of a lot of the things that I've always wanted to do. So that's my biggest, I guess, advice is, yes, you do have to be smart to some degree, but also you have to have that drive in order to, be able to buckle down when you need to and achieve things.
It probably helps too, kind of to surround yourself with like-minded people and, develop that social network that you're all equally motivated.
Yeah, definitely. I'm getting questions if I'm on LinkedIn. No, unfortunately, I think I'm only on Facebook. So my wife is married to someone on Facebook. Otherwise, I'm not big on social media. That's another way that I'm able to stay focused is don't give in to Twitter or the face pages or the LinkedIn's or the MySpaces. Other than playing video games in my free time. Otherwise I'll get distracted.
Well, and there's a question: how do you balance your work life?
That's a great question. And this is something that I definitely struggled with when I was first a postdoc, and I actually got burned out a few times. Some people, they will work many, many hours a week and for minimal or non-existent returns in some cases, unfortunately. And sometimes, I do have to work a lot if there's a big deadline or a big project milestone that I have to hit. But I realized though that, I was unhappy. I didn't like my job at some points, which was horrible because I was effectively, at my dream job at NASA. And I made a conscious decision to back off a little bit. I'm getting paid to work 40 hours a week. Don't try to force yourself to, fit in all this extra time. And I was a lot happier. And I also listened to what's called my customers at JPL, basically the people that were hiring me to do projects. None of them seemed to complain. None of them seemed to give me any feedback that they were, that I was missing any deadlines or anything like that. So I took that as okay, I can relax a little bit. I can enjoy this more. I did ultimately enjoy this more. I got more sleep, which was awesome. And I was still doing great work. And I was a lot easier to sort of fit my work-life balance. It is still something that I do struggle with a little bit. For example, the citizen science project, we have a Slack channel. And whenever I get new Slack messages, that comes directly on my phone. But I really try to disconnect on weekends and nights, for example. And having that disconnect is really healthy because it allows you to mentally reset. And then you come back to work on Monday or after a vacation feeling a lot better and a lot more rejuvenated, and you tend to work better rather than feeling overwhelmed all the time. So it's been a trial of errors, Jose, of how to balance that work life.
Let me ask you a question too about kind of going back to coursework and life skills. You obviously took a lot of science classes, but how important are the kind of what's some people call the soft skills, the speaking and writing and those type of skills in your day-to-day job as an astronomer?
Yeah, it's really important. Being able to basically describe your work and your research to the rest of the community is paramount to success in the community. So one of the ways you're going to be on a day-to-day, you're interacting with your peers. So at the very base level, you have to know to interact with other people. So I'm part of a very large team at JPL that works on CGI. I'm part of a smaller team that works on Exoplanet Watch. I see Rachel Zimmerman Brockman, who's one of the co-leads on Exoplanet Watches here. Thanks, Rachel, for calling in. And interacting with your team and managing your team are really important soft skills to have. But also, once you get the observations, once you make the big science breakthrough, you have to get the word out of your discovery or your new finding scientifically. And the way to do that is through published papers. That is the big way that our field gets new scientific breakthroughs out, is through the peer review process. So what you do is you write a paper, you give your background, your observing, your data analysis, your interpretations. You have to clearly sort of describe what you've done, why you've done it, motivate it clearly as well, and prove, beyond a series of a doubt as much as you can, that the finding that you found is correct and true. and you have to persuade your peers to accept that finding as well. So, even if you want to be an astronomer, my lesson is, or my advice is, don't ignore your English classes, for example, because, being able to write, being able to express yourself, to sort of explain what you're doing and why are really, really valuable soft skills to have. So luckily I didn't snooze too much my English classes. I can somewhat write, and that really helped me with being able to write, papers that explain my science, and now get cited in my field as a result.
What's the job interview process like that?
Terrifying?
Yeah.
Like any job interview process, it can be terrifying. So for example, you give a presentation on your work and your research, and then you talk with many different people throughout the day. They don't tell you who is on the hiring committee or not. So it's unclear out of the 8 or 10, 15 people that you personally talk to on a one-on-one, or are not on the committee. Sometimes you meet with small groups. So being able to sort of, to interact professionally and in a way that enables you to take even the most complex of scientific ideas and to boil them down so that anyone can understand them is really key. So to help me, force me to be able to do this better on science, I actually try to give the same exact presentations regardless of who I'm talking to. So if I use the same base slide packet, regardless if I'm talking to the public or even a scientific group. And that's to force myself to be able to take really complex ideas and to boil them down and to explain them, for example, to anyone in the community. And doing that and sort of forcing myself to do that, I think really has helped me out to become a better speaker, for example.
Have you now been on the other side of that, where you've participated in as an audience member in job interviews?
Yeah. So we actually just hired someone for the CGI Product Science team, and it was really fun to sort of see the flip side of that and sort of, make mental notes myself on, if I were to ever go through the job process again in the future, hopefully not, what I should or should not do. And you're always learning as well. I'm going to be basically a lifelong learner, which is a lot of fun. I love to learn. It's honestly a blast. And, learning through experience is one of the big key things that I've been able to luckily learn how to do here at JPL. And that's another key lesson learned, I guess, to use the word learn way too many times in this sentence. But basically, learning how to speak, learning how to write, how to convey my ideas, and how to manage a team, how to work in a larger team, to meet milestones. Those are all things I just sort of learned by experience here on Lab, and it's been a blast.
Carolyn writes, thank you for a fascinating insight into your career. And thank you, Carolyn, for tuning in.
So we're also getting questions about how is coding used in practical astronomy all the time. So typically when you get your observations from a telescope, it's in an image format, and then you have to convert that image into the measurements you want to make. So really, if you want to be an astronomer, coding is almost always a requirement. So for exoplanet science, it really seems like Python is the code language of choice, at least the code du jour of the day right now. But knowing any sort of coding background would be super helpful. Do you need to study astronomy in a subject in school to be an astronomer? In high school, definitely not. I know there's some high schools and grade schools that don't have astronomy as a subject. They actually just added it as a course in my senior year of high school. I think I'd already applied to undergrad programs. So you don't absolutely at all. You can definitely get that in an undergraduate program. In college, typically, it depends. If you major in physics or chemistry or biology, you potentially, or geology, for example, you can get a degree in astronomy or planetary science. So for example, in our PhD program, we had a lot of people coming directly from geology programs, studying rock formations and geology on other planets. And they adapted what they learned about Earth to other planets outside of our solar system, or even other planets in our solar system like Mars. So college, not necessarily, but typically in the field of astronomy, sort of the minimum requirement is a master's degree, and typically the preferred degree is a PhD. And typically those are planetary science or astronomy. Do I think if there's any life on exoplanets? I am very optimistic. I think so. Otherwise, I think this will be a large waste of space if there's not life out there elsewhere. Unlike the History Channel, I don't think we have had interactions with life either in the present or in the past, unfortunately. But yeah, I'm very hopeful. I think that there is life elsewhere out there in the universe.
How many years away do you think we are from finding life?
Ooh,
What's
that's a
the
great
over
question.
under on the?
Personally, I think we're probably looking at 2030s, 2040s. Maybe that's sort of optimistic as well. Hopefully James Webb will be able to look
Yeah.
for signs of life. If not, that might require the next generation of space telescopes that are, a little bit more precise than James Webb, or a little bit designed a little bit differently. So it's really unclear, and that's one of the biggest ultimate questions is there life? And then if so, when will we find it? It could be as soon as tomorrow, or alternatively, we might have actually already discovered the planet that has life on its surface. We just don't have the means to observe those signs of life. And what makes it also really hard is, just because the signal is there doesn't mean it is life, and vice versa. So the hardest part will be is demonstrating to the rest of the community and convincing them that this little blip in the signal of your planet is conclusively due to life. Because there's a lot of things that happen on the Earth that happen abiotically, that happen naturally without life. And, just because you see that same signal on an exoplanet doesn't guarantee that it formed due to life. It just might have happened naturally. So even when we get the observations, there'll be a ton of work involved to sort of vet those observations and to basically demonstrate that it is definitely life out there.
You kind of hinted at, another part of your job, and that is you have to be able to accept criticism. When you publish these papers or speak at professional conferences, not everyone's going to agree with your research results, correct?
Yeah, exactly. And that is one of the things that I struggle with as well. A bunch of us have what's called imposter syndrome, which would feel, it's basically the feeling that we're never adequate enough or never good enough. And that is always in the back of my head, saying, well, Rob, you're doing this, but you might be wrong. And rather than letting that dominate my thought process and take me down, I use it as a asset, in the sense that it forces me to double check my observations, to check into my results, and to make sure what I published isn't wrong. And and basically being able to persuade the rest of the field that your finding is correct. It can be a daunting task at times, and
you're putting yourself out there. It's not an easy thing to do. What are some of the best resources other than programs like this for students who are looking for additional help?
Well, definitely plug your local library and science museum. That's definitely how I got involved, and that fostered my love of science, of NASA, from a young age. So definitely check out your local resources. If you don't have them, you can go online. There's a lot of great resources now online that I wish that I had as a kid. For example, there's the NASA exoplanet website. Just Google NASA and exoplanets, that'll pop up. There's tons and tons of great hands-on resources, animations that sort of describe and explain exoplanets. And also, they give really cool insights to all the other cool work that's happening in astronomy and planetary science. So really, the internet is an excellent, excellent resource that you can use to interact directly with astronomers and planetary scientists, NASA employees, engineers. But also, we're making multimedia, we're making products all the time that are aimed directly at the public to help educate everyone, to sort of explain what we're doing on a daily basis.
All right, we got time for a couple more questions. John asks, will this presentation be posted on the library website? Yes. Yes, that'll be probably posted early next week. I've got some edits to make. When I gave my introduction, I still had my microphone muted. I need to edit that out, but yeah.
No worries. It's happening all the time in these weird COVID times. I definitely have done that myself many times.
I'm glad you said something. I was talking with Dr. Zellem before we began. I usually have a colleague here with me, and she would always jump in really quickly. And Ollie has a question: do you interact with local national media? JPL certainly gets, NASA certainly gets media attention.
Yeah, and I was lucky enough to work on a study with actually one of our interns. She published a paper that she very nicely included me as a co-author on, and she actually got a press release from her really cool observations and an analysis of exoplanets, specifically looking into their clouds on these planets. So she was basically studying weather on planets outside of our solar system. And very cool, I was able to be part of the press release and get interviewed for that process as well. And yeah, JPL has a really excellent communications group. I work with them on the citizen science project, for example, and I help out as one of their subject matter experts. So if they have questions for a review of an article or a press release, or if they have any questions about anything, I'm really lucky that I get to be part in that process, because I love talking about what I do and sharing my love of astronomy with the world. And I'm really lucky that I get to do that, and get to do that through JPL.
You also mentioned artists working at JPL, and I love their exoplanet artwork. Do you work with artists occasionally?
Yeah, so actually JPL has its own art department actually on lab, and they actually started off doing a lot of installations on our campus that were really cool art installations, and they're directly involved with JPL, but also they make a lot of public facing things as well. So for example, a bunch of you hopefully saw those exoplanet travel posters, and those were made actually as decorations on lab. And then they got so popular on lab, they decided to release it to the public. And apparently it actually broke the internet and shut down a few of the JPL websites due to all the downloads. And those travel posters are really cool. They're like in the Art Deco style from like the national parks from like the 20s era. Those are really cool posters. And I was lucky enough to, when I got to JPL, to help out with their the planet Galaxy of Horrors posters. So these are like, sort of like movie posters and that like 1960s, 1970s slasher film horror movie posters, which are pretty cool. And I was basically one of their subject matter experts with myself and a few other scientists that sort of gave them ideas and talked about the science to help inspire them to make these posters. So it's really gratifying. I'm also helping out with the communications team on the Nancy Grace Roman Space Telescope. Over this past Valentine's Day, they released a bunch of Valentine's Day cards talking about Roman. And one of my horrible puns, "You're the apple of my CGI," was actually accepted as one of their really bad Valentine's Day cards. So it's pretty cool to see, something a really bad dad joke that I came up with actually made it as a Valentine's Day card. And I hope that someone gave that card and got a great eye roll from whoever they gave it to.
Yeah, I can imagine it's pretty popular, actually. We're approaching the top of the hour, and Dr. Zellem needs to get back to work. Let me ask you one more question.
Sure.
Kind of the first thing that pops into your head. What's the one thing you know now about being an astronomer that you wish your high school self would have known? If there is something.
That is a great question. It's kind of hard to whittle it down into one thing. I don't know. I think just knowing as a high school kid that, eventually I'd be working at NASA, that would have blown my mind. It's been my dream come true. And I'm really, really lucky that I get to work at JPL, and maybe just to never give up, that all my hard work will pay off and that I'll eventually get, to where I want to be. And it's honestly, I'm really blessed that I get to work here. It's absolutely a ton of fun, and I'm happy and honored that I get to interact with the public as well. So thank you again to everyone who called in today, also for your excellent questions. If you have any other questions, you can also Google me. I'm the only Rob Zellem in the world. If you add NASA, you can actually go on my own personal website, and there's a way to get in contact with me through a forum. So if there's a question you have, about my career path or something wasn't clear, feel free to get in touch with me. Also, we would love for the amateur astronomers and citizen scientists on the line to please join our citizen science project called Exoplanet Watch. So just Google NASA Exoplanet Watch, and we would love to have you participate in this project.
I'm
Otherwise,
looking
thank
forward
you
to
so much.
joining that. So yeah,
Yeah,
thank you, Dr. Zellem, for taking the time to talk with us today about your fascinating career. Really, really appreciate it. And I want to second what Rob said. Thank you, everyone, for tuning in today. And if you want to know about the library's upcoming events, go to lindahall.org and you'll see a number of events. And we're going to have some space-related programs as well coming up later this year. So be sure to check it out and hope to see everyone back here soon. So thank you and have a great rest of your day and a great weekend.
thank you so much for having me again, and have a good one, everyone. Stay safe.